My name is Andreas Malikopoulos, Cornell University. We have 4 talks designed today to cover the broad topic of on mobility equity. You will hear different topics around how we can create an affordable accessibility system that can be fairly distributed across a transportation network. So one of the talks will cover topics related to how we can use emerging mobility systems in specific scenarios, traffic scenarios, with focusing on equity. Another talk will cover multimodal transportation systems and how we can have a fair mobility system. The third talk will talk about a metric, how we can come up with a mobility equity metric that can sort of measure these entities. And the last talk will get to how we can use connected automated vehicles to cooperate with respect to improving mobility equity. At this point, I would like to call my colleague, Rafi Stam, to come and chair the session and also present the first presentation. Thank you, Rafi.
Thank you. Thank you, Andreas, for organizing this tutorial session and putting in all the work. Thank you for getting this awesome lecture hall. My name is Rafi Stern. I'm an assistant professor at the University of Minnesota. I was asked to do a tutorial on sort of traffic flow, automated vehicles, emerging technologies. So this talk is sort of focused as a tutorial, but also talking about my work. So I'm going to try to weave in what other people have done and sort of give a sense of, I hope that this is maybe approachable for people who aren't deep in the weeds of traffic engineering. And so what I want to talk about is mixed autonomy traffic and look at how we can maybe use that, control that, steer that into a sort of a way that is beneficial not just for the people in automated vehicles. So what are the benefits of automated vehicles? There's a lot of sort of different ideas out there for what this might be. I did a Google search, came up with this Forbes article, so very public-facing, 5 ways that self-driving cars will make the world better. Safety, parking, right? You don't have to park your car anymore. Your car is safer. Making the commute easier. You can maybe, we've gotten used to work from home. Why not work from car, right? Emissions, with the big caveat in the list that only if the cars are electric. And I'm like, well, I'm not sure that has anything to do with them being automated. And reducing the need for air travel. You don't have to go to the airport anymore. And what strikes me about this list is these are 5 ways that an automated vehicle might make your life better if you own one. Right? And a lot of the benefits that we see for vehicle automation are sort of advertised for the person who sits in the car. The problem is that automated vehicles, at least for the foreseeable future, what you're imagining, sort of this picture at the bottom there of an automated vehicle, is likely going to be quite expensive. Between the sensors, the additional sensors that are needed, the additional compute power that's needed, the proprietary algorithms that are needed, this will not be something that is intended for everyone. This will be something that is really intended for people who can afford to buy that. We'll get back to that in a second. But the way that I want to look at this is, OK, but how can we use them to sort of make conditions better for everyone, even if they can't afford an automated vehicle, even if they're stuck in their regular car like I am? So the thing that I'm really interested in, the thing that I want to talk about is traffic jams. And how will automated vehicles impact traffic flow, and how can we use them maybe to ameliorate or alleviate some of the negative effects of traffic jams. Traffic jams are very common. There's a lot of reasons for traffic jams. Construction, a crash on the road, some sort of reduction in capacity, some sort of bottleneck might lead to traffic jams. The ones that I'm talking about and the ones that I'm really interested in are what I call phantom traffic jams. These are traffic jams that arise for quote unquote no good reason. We see them here on the left, sort of happening on an open road in the wild, as I like to say, and then on the right in an experiment. You might have seen this video before. It's a group of researchers in Japan. I love this. Traffic engineers were debating over whether or not these phantom traffic jams were real things. A group of physicists said, let's just do an experiment and see what happens. And so they came up with this setting where you have sort of no external factors. It's just pure traffic. Infinite traffic. It's a ring of 22 vehicles. They start at the same speed, same spacing, so at like an equilibrium flow, and relatively quickly the stop-and-go wave emerges. And what's really happening here is what we call string unstable traffic. And the question of string instability is what happens to small perturbations from an equilibrium flow. The equilibrium flow here being all the vehicles driving at the same speed and same spacing, so 0 acceleration. and then you see one perturbation. I think there's a common misconception. It's not the question of what happens to the individual vehicle. Naturally, any reasonable driver is going to return to their original speed, keep driving. That's not the question of string stability. That's sort of maybe some sort of asymptotic stability of the driving. The question of string stability is what happens to the perturbation. And so in string unstable traffic, you can imagine that initial small perturbation amplifies from vehicle to vehicle, even though each vehicle originally goes back to that, like that equilibrium flow is recovered, the perturbation amplifies, as opposed to string stable traffic, where that initial perturbation is going to dissipate. And there's a lot of ways to address this question of string stability. One popular way that's been purported a lot, and that, in fact, I've seen a lot of really good talks this week here on this topic, is platooning. So the idea with platooning is you have all the vehicles use the same automation technology. This idea has been around since the 90s. So this is an experiment done at the University of California in the early 90s with platooning. All the vehicles use connectivity, and all the vehicles have automation, and they communicate with each other to maintain very small headways, very small inter-vehicle spacing. And the benefit here is really clear. These vehicles can drive much closer together, can brake very suddenly, so safely do that. You see 2 to 3 times increase in throughput. From a traffic or transportation management perspective, that's amazing. You've basically built a road on top of a road on top of a road without actually building any new road. Without paying for any new construction, you use technology alone to triple or double your capacity. That's huge. But the drawback, and this sort of gets at my overarching theme here, is it's not for everyone. It's for those who have platooned vehicles. And in fact, one of the ways to address this, if this does happen, there's a lot of proposals for dedicated lanes for platooned vehicles, which is great, again, if you have one, but not necessarily great if you're just a regular person stuck in your regular car like I am. So I think this is an important time to sort of differentiate between different types of automation. I've used the term automated vehicle very loosely in the first 5 minutes here, but I want to define that a little bit more concretely. You may have seen this before, but there's basically 5 different levels of automation. There's level 0 automation, so I guess 6 in total. That's what I personally drive. That is your regular car. So steering, acceleration, that's the human driver. Monitoring the environment, that's the human driver. If something goes wrong, I'm there to slam on the brakes or swerve to avoid hitting something. There's no robot. There's no robot in control. As we go to low-level automation, level 1 driver assistance, we start to take some of those driving tasks and hand them over to the vehicle. And as we go up to higher and higher levels of automation, we're handing more and more of those driving tasks over to the vehicle in more and more driving contexts, so in more and more situations. All the way up to level 5, full automation. This is what I think a lot of those benefits are being talked about. That's sort of the Google car. There's no steering wheel anymore. You tell it where you want to go, and it takes you there. OK, so while these higher levels of automation may happen a little further down the line, they're not really here yet. And so the first question I want to look at is, what's going to happen with these lower levels of automation? How will they impact sort of that general traffic experience for all drivers on the road? And then how do we address that with lower levels of automation? Specifically, I'm really interested in levels 1 and 2. A lot of people say, well, these are kind of boring. They've been around for a while, things like adaptive cruise control. Again, you're taking some of that driving and handing it over to the vehicle. And the question is, how does adaptive cruise control impact string stability? Now, if you had attended ECC maybe 15 years ago, you would have probably seen a talk that says adaptive cruise control is very easy to make string stable. There's a rich body of literature going back to the 90s, really, that looks at string stability and adaptive cruise control. And it turns out that these systems are relatively easy to make string stable. So they will not amplify perturbations, and they will nicely dissipate perturbations. OK, so the first question that I had a couple years ago was, OK, but when I rent a car with adaptive cruise control, I don't like the way it drives. I don't actually think it's doing what the literature says it ought to be doing. And so in order to sort of ask that question of how will these vehicles impact traffic flow, we need to first be able to look at a vehicle and say whether or not it's string stable based on its behavior. I'm going to just go through a little bit of background on traffic modeling and background on string stability analysis to sort of have the computational mathematical tools to be able to analyze these vehicles for their string stability behavior. So in order to model traffic flow, engineers love these things called what they would call microscopic car following models. You might just think of them as an ordinary differential equation that describes the acceleration of a vehicle as the state, as a function of the state. And the state is the inter-vehicle spacing, the spacing between the vehicle that we're looking at and the vehicle in front of it, the relative speed, so the rate of change of that spacing, and the speed of the following vehicle itself. And for vehicles that sort of drive like normal vehicles, they slow down when they get closer to the vehicle in front of them, et cetera, it turns out that we can look at that equilibrium spacing, where they all have the same speed, same spacing, i.e. no acceleration, and look at what happens with a small perturbation from that equilibrium spacing, and we can sort of look at how that propagates from one vehicle to the next. What we're going to do is basically we're going to linearize around that equilibrium and then observe what happens to that perturbation. And skipping sort of a couple of steps, it's relatively straightforward, but we get to this really nice result that says that if we look at just the partial derivatives, if you're comfortable with just a linearized stability analysis, we can very easily compute whether or not this particular vehicle is string stable. All we need to do is we need to have the car following model that describes the vehicle. So if we have the car following the model that describes the vehicle, we can easily run this stability analysis and say whether or not it's string stable. So the next thing we need to do is build car following models for these vehicles. So the idea is basically not to capture what's programmed on the car, but to capture how the car actually behaves, right? And there's a difference there. There's a lot of nonlinearity in things like the engine, the transmission, et cetera. And so even though the car might be programmed with a certain, I don't know, PID or some sort of maybe more fancy control, that's not necessarily the behavior that we observe. And so what we need to do is we need to come up with a model that nicely describes that, and then calibrate that model based on real driving data. OK, so the model that I'm going to use here is one that's really common in the literature. It's an optimal velocity model with a relative velocity term. Some people call it a constant time headway model. If you learn to drive and we're told to always leave a 2-second time gap or a 3-second time gap between you and the vehicle in front of you, you learned this model effectively, right? You learn to keep a 2-second rule. And if you look at the literature on these linear string if you look in the literature on adaptive cruise control, a lot of the controllers are based on a constant time gap policy. So this is a pretty common assumption. We collect a bunch of data on this. So what we do is we have a lead vehicle that drives and a following vehicle that follows with that ACC turned on. And it's just following the vehicle in front of it with its adaptive cruise controller. We get GPS data for the lead vehicle and the following vehicle, and so we can see the spacing, we can see the speed of each vehicle, compute the relative speed. So if you look at the data, you see, small speed fluctuations. For the lead vehicle, you see what the following vehicle does, and then for another example, and then you can calibrate this type of model. And I've done this for probably about 8 or 9 different vehicles at this point. And when you look at the calibrated models, you can then look at the string stability of those models, and it turns out that sort of basically all the vehicles I've looked at are string unstable. So that's the best way I have to display that, to convey that. There is a little bit of good news here, and that is that I've recently looked at a couple of electric vehicles, and it turns out that those vehicles this is basically not true. Those things are as close to string stable as anything that I have seen. I have some speculation as to why that is. I think part of that is you're cutting out a whole bunch of nonlinearity in the engine dynamics and the transmission dynamics. You also have instantaneous torque, or basically full torque instantaneously, basically. And so you can much more precisely drive these controllers that were intended to be string stable. Though I'm open to discussion and learning if somebody has a better hypothesis. OK, so now let's get back to the big question of what does this mean for everyone in the traffic flow? What does this mean sort of from you're driving in the traffic flow, you don't have an adaptive cruise controller, you didn't pay up to get that feature, but what does this mean for you, right? What does this mean from like a general population perspective? So we can look at this in simulation. We have now built these very accurate models that nicely describe how they behave. So let's look at what happens in simulation. We look at both sort of theoretical, if you look at the literature, what they say adaptive cruise control, what they say automated vehicles ought to behave like. And we can look at the models that sort of represent the realistic car following behavior of real adaptive cruise control vehicles. In order to understand these, I'm going to go on a small detour into a little bit of traffic flow theory. Again, this is a tutorial, so I'm trying to sort of bring in some ideas that maybe you've seen this, maybe you haven't. But to describe traffic flow and traffic behavior, we look to the 1930s when this guy, Bruce Greenshields, at the University of Ohio, had this idea that that the speed that traffic is traveling at ought to depend on the density of vehicles on the roadway. Now, this was the early 1930s. There were not a lot of vehicles on the roadway. So he went out and he collected data with a camera where he took pictures to estimate how fast the vehicles were going and what the density was. And he got a lot of low-density measurements. And he got one high-density measurement. And he did what any good engineer does, is he drew a straight line between them. And he came up with this speed-density relationship. Now, flow is speed times density, which means that if you have a linear speed-density relationship, you're going to have a quadratic flow-density relationship. Most engineers, though, looking at data, they say it's probably something closer to triangular. But either way, basically, at different densities, you have different flow. You have a uncongested or a free flow regime where additional vehicles don't really interact with each other. And so the higher the density, all you're doing is you're increasing the amount of flow up until some critical density, at which point you reach the maximum flow, or your capacity, and then you get into the congested regime, where vehicles have to brake to avoid each other, et cetera, and traffic jams sort of arise naturally. OK, so with this in mind, what I want to do is I want to look at fundamental diagrams for different market penetration rates, or different percentages of vehicles with different types of automation, and see what happens. OK, so if we look at fully automated vehicles, it's hard to tell, but you do see a small increase, and that is consistent with the literature. So these are models that behave like what we are told we ought to expect fully automated vehicles to behave like. And sure enough, we see an increase in capacity. If we look at the adaptive cruise control vehicles, so this is 0%. This is all human-driven. This is sort of what you would expect. We see our nice free flow regime, our congested regime, and a capacity somewhere around here. And if you look at higher percentages of commercially available adaptive cruise control vehicles, what you see is two main things. You see sort of a collapse of that fundamental diagram, which means that the maximum roadway capacity goes down by maybe 20, 30%. And the critical density, i.e. the density at which congestion sets in, moves to the left. So at lower densities, because these things are quite conservative, we start to see congestion arise. So that's quite different from the promise that I made of 2 to 3 times capacity with these vehicles. OK, so the next thing is I want to sort of review what's been done to get towards that. And so the idea is we want to drive the AVs to be better. Right? We want to drive them so that they improve the traffic and don't necessarily sort of make it worse. OK, so in order to do that, we need to come up with a model of and the other thing that we want is we want them to drive not too differently. If they drive too differently from humans, they're going to do something that's weird. So we're basically going to start with how we observe humans to drive, and then just add a feedback control term. So this might seem like it's cheating. This is pretty straightforward. To drive with some desired or equilibrium speed. So we want to look at what's the average speed of traffic, and then we want to kind of maintain that speed. And if you look at this in if you look at that same ring road scenario that I showed you originally, this is actually a really straightforward sort of intro to controls type problem. It just becomes pole placement, basically, right? You pick your gains, and you're off to the races. OK, and it turns out that this is a really easy stabilizing control. And if you implement this in simulation, this actually works really nicely. So on the left-hand side, the blue vehicle, well, all the vehicles are the same. And you'll see that relatively quickly, those same stop-and-go waves emerge. It's just because we've calibrated those vehicles to drive like they do in reality or observed. On the right-hand side, that blue vehicle is autonomous capable. Currently, it's switched off, and you see those same waves emerge. And then in a couple seconds here, we're going to switch it on. And you'll see that it's going to drive with that controller, that feedback controller that we saw a minute ago. And it's going to relatively quickly stabilize that flow of traffic. And so now we've turned on the AV. And what you see it does, it got turned on at a very opportune time. And so it didn't race to accelerate to catch up with the vehicle in front of it. Instead, it sort of slowly accelerated towards its desired speed and then stayed at that. OK, the reality of how to implement this on an actual vehicle is a little harder. You can't quite do that. And so a couple years ago, I worked with a number of folks, some of whom I believe are in the audience, to design controllers that could actually be implemented on actual cars. One of the challenges is that most vehicles, you can't implement an acceleration. Those are all acceleration controllers. Most of what you see in the literature is acceleration-based controllers. But you have to implement a speed. But we were able to come up with something that, in spirit, really captures the same behavior. And the result, I'm just going to show you sort of the video that describes this, is we redid that ring road experiment. Very similar to the simulation I just showed you. The vehicle with the arrow on top of it is autonomous capable, but it starts without autonomy. So it starts as a human driver. The speeds are at the bottom. Relatively quickly, those stop-and-go waves emerge. At this point, we've activated the autonomous vehicle controller, and it very quickly is able to do what it did in simulation and smooth the traffic. And so when we look at the results, at the top we have a space-time diagram, what traffic engineers call a space-time diagram. It's just the trajectory plots of all the vehicles. You can see very nicely here where those stop-and-go waves emerge. And then once we have smooth flowing, once we've activated the vehicle, we have that smooth flowing traffic. And this has pretty big implications. This is back towards improving the traffic for all. We've changed the behavior of one of the vehicles on the road. And we've then changed the traffic flow for everyone. We had, on that experiment, we actually had little sensors on each of the vehicles that measured the onboard OBD2 onboard diagnostics. So we're getting real-time fuel consumption information from each vehicle. And the reduction in fuel consumption was kind of surprising. So unsurprisingly, you see a small increase in throughput. On average, the vehicles are going faster. You see a decrease in braking, which is sort of like a proxy metric for safety, right? Harsh braking events mean that if you hadn't hit the brakes, you would have had a collision. But what was really most astounding to me was the reduction in fuel consumption. We saw a nearly 40% reduction in fuel consumption. And now, that seems high, and I was convinced I had done the math wrong when I first saw that. But we're comparing the absolute worst case scenario for all the traffic to the absolute best case scenario from a fuel consumption standpoint, right? Stop and go waves to coasting is the worst of the best. So could you actually see that big of a reduction across traffic generally? Probably not. But the nice thing about this is we've leveraged a small number of automated vehicles to really impact the flow for everyone. OK, I've got about 5 more minutes, but I should probably leave a couple minutes for questions, right? OK, so the next thing is, what about our legacy infrastructure, control infrastructure? Ideally, if we're thinking about this from so traffic flow will change, right? Whether it's ACC vehicles or highly automated vehicles, traffic flow will change. Our control infrastructure is built for a certain type of traffic flow behavior. How do we modify that to stay relevant and sort of provide benefit not just to the people in the automated vehicles, but to all the road users who are using the highway? And so the vision sort of that I want to briefly present here is we need to fight congestion with the AVs we have, not the AVs we want, right? So ideally, we would be able to somehow observe what the traffic dynamics look like, so who's in the flow, then come up with some sort of, based on the current makeup of automated human drivers, whatever, what do we expect that fundamental diagram, that flow density relationship to look like? And then whatever control infrastructure, here I've showed ramp metering control, but whatever control infrastructure you're interested in, you can then modify based on the current observed flow density relationship and not some static flow density relationship that comes from sort of the last 20 years of observations, which is what's done today. OK, I'm going to, in the interest of staying on time, going to sort of go a little faster here in the next couple of steps, but I'm happy to answer any questions if there's questions at the end. OK, so what we need to do is let's imagine that we can do this. This first part, just imagine we can do this. We can look at the flow based on how they're driving, identify what type of vehicle they are. Are they automated or are they human driver? There's a lot of sort of ideas for how that might happen. But imagine we know that X percentage, 20%, 30% of vehicles are automated, now what? So we need to be able to come up with some sort of joint flow density relationship for that composite flow. We can do that by basically looking at the equilibrium. Sorry, we can look at sort of an average density based on the fraction of vehicles of each type, and then come up with and I'm going to skip through this, unfortunately, relatively quickly, but come up with a combined flow density relationship that depends not only on the flow depends not only on the density of vehicles, like it does now, but also on the fraction of vehicles that are automated. So what we have is effectively like a three-dimensional fundamental diagram. We have a fundamental diagram that depends not only, or a flow that depends not only on density. So if you slice it right here, that's just your standard flow density relationship, but also depends on the penetration rate or the market penetration rate of automated vehicles. In this case, I'm looking at it, I've represented it for ACC vehicles, so it kind of decays. But if you imagine for fully automated vehicles that we might have in the future, this would increase with higher penetration rates of automated vehicles, right? And so now, as an example, let's just take your standard ramp metering control. That's a pretty standard control. And modify it to not just look at a static target density. The idea behind ramp metering control is basically that we want to have, it's a feedback control where we control the on-flow of traffic such that the resulting downstream flow rate is at or below the critical density, that transition density from congestion to uncongested to congested traffic. And instead of looking at a sort of constant critical target density, we can look at a target density that depends on the market penetration rate of automated or adaptive cruise control vehicles. So now we've basically switched this to have a market penetration rate dependent critical density. So I'm going to look at three different scenarios. One is uncontrolled, so that's just allow whatever can get on the ramp. That's no ramp metering. Then I'm going to look at scenario 2, which is controlled, but assumes a fixed fundamental diagram. And then the third scenario is controlled with a market penetration rate dependent fundamental diagram. We implemented this in MATLAB very simply here. Excuse the graphics. But I think the result is at the bottom. So uncontrolled, unsurprisingly, has if you look at the total system travel time, or the total time spent, rather, we see about 4.4 hours. And we can reduce that down to about 4.3 hours with simple ramp metering. And we can reduce that down another 5% or so with, or 4% or so, if we look at the actual sort of if we look at the market penetration rate dependent fundamental diagram. And if you look at the densities, you see that basically you go into congestion with both uncontrolled, you're going to have congestion, and even with the controlled, but if you're using the wrong static fundamental diagram, but if you use this adaptive fundamental diagram, then you're able to, even that simple feedback controller is able to nicely avoid that congestion scenario. OK, so in summary, I think increased vehicle autonomy will change traffic flow dynamics. That will have an impact on not just the road users who are in the automated vehicle, but also the road users who are around them, because they're stuck in the same flow. Remember, you're not in traffic, you are part of traffic. Right? And if other people are driving differently, that's going to affect the traffic that you are part of. So to benefit society, I think sort of my charge to us is let's think about not just the vehicle occupants, not just the people driving the vehicle or in the vehicle, but also the traffic flow around it and how those vehicles impact the rest of the traffic flow. There's a whole bunch of different games you can play. I showed one example with ramp metering, but I think there's thousands of different examples of how you can think of, OK, how does this change control for traffic systems? Thank you again. I think I'm right at 10:30, so I'm probably out of time. But maybe I'll be around at the break afterwards if there's any questions.
Absolutely.
Thank you.
Thank you, Rafi. We can perhaps entertain one quick question while Mauro is setting up his laptop. Any quick question that Rafi can address? Yes.
Yeah.
Cecilia, just wait for the mic.
Yeah, thank you.
Thank you. Thanks for the presentation. That was very nice. So I would just, I have a curiosity. When you estimate the fundamental diagram by vary the different penetration rate, you are considering a time gap that is lower than the human driving vehicles standard, or you have also considered to vary the time gap between vehicles?
It depends. So basically, we just think of it as, you have let's say a T sub A for automated vehicles and a T sub H for human vehicles, time gap for each, and it can be. So they're not necessarily the same, or generally we assume that they're not the same. They could be the same, right? But the framework allows us to do either assume it's bigger or smaller. So in the case of ACC vehicles, if you look at the data for how they drive, you have to assume it's bigger. Whereas in the case of what I assume automated vehicles will be able to achieve, you can bring that down, and then it's less than human drivers. But either way, there's the flexibility there to consider either one. Does that answer your question?
Yes.
OK. We can talk offline afterwards, too.
Let's thank Rafi once again.
Thank you.
So Rafi gave us a very nice overview of what we can do using autonomous vehicles to smooth out the traffic flow and have direct benefits. Now Mauro will elevate us and take us to the multimodal transportation and how we can use multimodal transportation for equity.
So, thank you so much, Andres. Mauro Salazar, I'm an assistant professor at Eindhoven University of Technology in the Netherlands, in the Control Systems Technology section. And this is joint work with my master's student, Sara Betancourt-Giraldo, and my PhD students, Leonardo Pedroso and Fabio Paparella, who's also sitting here in the audience. So I guess we all know we've been facing quite some challenges in mobility. You can see in these red boxes. There's user dissatisfaction, pollution, congestion, and so on and so forth, right? And that hasn't changed for the past decades. At the same time, we're witnessing the advent of new technologies that could give us actually some nice opportunities to face these challenges. And here you can see autonomy, connectivity, electrification, and so on and so forth. Right? And the question is, how do we combine all these technologies to address the challenges? Because if you do it in the wrong way, you could also have setbacks. Think about what transportation network companies have done to urban traffic in major metropolitan areas. So the question is, okay, how do we combine these technologies to address these challenges and design future mobility systems? Right? How do we combine autonomy, connectivity, electrification, but also technologies that are already there since some years and are older than the train? Right? So if you combine autonomy, connectivity, and electrification, one of the paradigms that has emerged in the past decade is called autonomous mobility on demand. Autonomous mobility on demand is very simply said, a fleet of electric, potentially electric, hopefully electric, robotaxis that provide on-demand mobility. Right? And the question is, okay, is this the way to go, especially in urban environments? Will this kind of solve the challenges I've mentioned before? Well, for as smart, as clever these systems are, you can centrally control them, you can schedule their charging very efficiently, and so on and so forth. They're still cars. And cars have some drawbacks. And one of the main drawbacks they have in urban environments is that they use a lot of space. From a space efficiency perspective, they're very bad, right? You could take these 200 people and put them on public transit. And then the situation would change enormously, right? However, public transit is not point-to-point. And though it still has this kind of very nice features that driverless cars are promising. This is a tweet by Amtrak, people talking about the future with driverless cars, where you can sit back, relax, and so on. They're talking about trains. You're so close, babe. Go find a train station. Now, if I may say, especially if it's Amtrak, well, good luck finding a train station. And anyways, it highlights the fact, public transit, you have to go to the train station, right? So it's not point-to-point. It doesn't pick you up. There's another dimension, which is the most sustainable way of moving, which is cycling. And actually, I did some back-of-the-envelope calculation the other day to look at the life cycle analysis. So take this with a grain of salt. Turns out that cycling is more efficient than walking, also in terms of life cycle analysis. And it's a great way of moving, right? It broadens your accessibility range, but of course, not everyone can cycle, and it doesn't cover long distances. So what I'm hinting at, why don't we take the benefits of all these worlds and combine them in an intermodal mobility ecosystems, which we can call intermodal autonomous mobility on demand system, where we combine the benefits of all modes within this integrated system. But to understand the potential improvements, the benefits of this system, we need to kind of start modeling it. And that's what I want to present today in this tutorial. So the way you can model this system from a mesoscopic perspective for a city is using network flow models. And network flow models, basically, you represent your city as a graph. The nodes are intersections, the arcs are road links, right? And then you do two things. Since it's a city, you have a lot of flows, a lot of people moving around, so you look at them as fluids, using continuous variables, okay? And second, we take a planning perspective, which means we look at demand, which is time invariant. We look at a snapshot, rush hour, and then you have a continuous flow of users that want to go from A to B, a continuous flow from B to C, from C to D, and so on and so forth. It's a steady state. So your metric is users per unit time, vehicles per unit time, because we're in time variant, and again, remember, mesoscopic perspective, therefore we look at flows. Okay? And this has been studied a lot. Here just some of the main authors that contributed to this, and with different flavors. It is very nice, it scales very well. It doesn't increase if you augment the number of users, so it's a very nice way of representing urban scenarios. And you can also add public transit if you want, the same way. Your nodes are the stops, the arcs are the legs in between. You can have also a walking graph, a cycling graph, and then basically model the fact that you can walk, then you pick up a car, it drives you, then you take public transit, right? You know, these nodes may be at the same geographical location, but they're different nodes. And this way, you don't need binary variables telling you whether you're on mode A, mode B, mode C. Everything is still linear. Now, mathematically, since it's a tutorial, how do we represent it? One thing to do, and this is something we recently did in the last paper, the third paper, you see there you can take a municipality. This is Eindhoven. So this is the city center here. And you can split it into regions. For instance, the postal code numbers, right? There you see 5623 is a region NR. It has a population of NR people. And then each of these regions has some demands daily, where people want or need to commute. It can be an hospital, it can be job opportunities, and so on and so forth, right? Which we denote with this triple, OM, an origin node, a destination node, DM, and a flow. Remember, we are looking at users per unit time, alpha M, that tells how many people per unit time want to go from OM to DM. And these are demands for region R, and we collect them in this calligraphic MR. And we do it for each region. Here you can see an example. You have these three origins, and then the squares represent the destinations. You can see bigger squares denoting more people want to go there in the city center, which makes sense, okay? Now, what else do we need? Which other ingredients do we need? So another ingredient is travel time. How long does it take you to cross any arc A? And depending which arc it is, if it is a car road arc, you will look at how fast it takes you by car. If it's a mode switching arc, you can see how long does it take me to board public transit, so how long do I have to wait, and how long does it take me to switch physically. You can still, if you keep travel time constant, you can still capture exogenous congestion effects. So if you're in the rush hour, TA will be higher. If you're not, it's going to be lower. What we cannot do in the contribution we'll present today is to change TA as a function of our choices, because we basically break convexity. Yet in other contributions on this topic, with some colleagues, we did manage to create endogenous congestion models. So today, TA is considered to be constant for the time window we're looking at, okay? And we need two optimization variables. The first one is a flow vector, which basically tells you for each demand M, how many users are traveling on arc A. We call it XAM, okay? So we have a collection of these XAM vectors that tell you where users are going, basically. We have to choose this from a planning perspective. How do we operate the system, right? This also captures the movement of user-carrying vehicles if you assume one user per car, okay? In addition, we also have empty cars that rebalance themselves, realign themselves to the demand distribution. We model them with vector XR. Same idea, XRA tells you how many empty cars are traveling on RK, only on the car graph per unit time. Everyone with me? Okay, good. So these are the two, that's it. Then we apply mass conservation equations with a steady state, right? So for each node j, every user entering it exits it. So these indicator functions tells, okay, if I'm at an origin, I have an injection of users, if on destination, an injection of users, and for the rest, I just look which arcs enter my node. Same for the cars, though we keep them in the system, we don't introduce or take them off, just summing over the rebalancing flows plus the user flows, right? Which represent user-carrying vehicles. Flows cannot be negative, pretty trivial. You can also have a bound on the number of cars. So our units are users per, or vehicles per unit time. If I multiply by travel time, I have the number of vehicles around. And you can also have, which we use in those two papers you can see there, congestion models. So if you want to have a threshold congestion model linear, you can say, okay, I don't want to increase congestion more than this point. You can use these linear inequality constraints on the Cardi graph. And then what you usually do, you want to minimize how you operate, you minimize travel time, maybe some operational cost, right? And then you find basically the operation. You can see this is overall a linear program. So you can solve for very big cities. We took Manhattan, we took Berlin, and we solved. And one result I want to show you is what are the improvements if you go from an MOD only car operation, to an intermodal setting. What are the improvements? And they're gigantic in terms of CO2 emissions, operational cost, and travel time, which tells you in the future, MOD doesn't have to be something on its own, it has to be integrated within an intermodal mobility ecosystem, okay? However, I was always wondering, we always look at time is money, and I was always wondering, are we optimizing for the right objective? I mean, if you look at literature, 99% is minimizing travel time. And only recently we've been seeing some deviations from it, and we'll see it also in the next talk. But are we optimizing for the right objective? Is minimizing average travel time what we want to do? So I decided to take a step back, also challenged by great colleagues like Professor Karel Martens from Technion. So I'm gonna, I wanted to kind of rethink what's the main purpose of transportation. This brings us to analytical philosophy, right? And the concept of justice, which Karel then translated to transport justice. So what's the purpose of transportation? Well, it's to provide accessibility, right? To opportunities, to jobs, to hospitals, and so on and so forth. What is accessibility? It's freedom to get to places, right? The possibility of and it's a multifaceted, complex concept. It's very difficult to implement. What is very interesting, what in the social science literature is being said, is any simple approach to capture it would already be good. Something that transcends only minimizing travel time would already be good. Okay? And one way is just could be the number of relevant destinations you can reach within a reasonable time threshold, right? So let's look at it mathematically. Basically, you have a time threshold, Tmax. Let's go back to the engineering world. Okay, Tmax is the maximum we can travel. And then we say, okay, if we have trip m, we have a binary variable, bm. It's 1 if our travel time, which is basically time times the flows by the total flow, is below the threshold, and 0 if you're above. We can all do a very nice BKM formulation if we're trying to maximize the number of BMs, right? If BM is 1, the equality on the right holds. And if not, it doesn't have to hold, right? We sum all the binary variables for each of the regions, and here comes another aspect. In transport justice, the idea is we want to follow what is called the Foster-Green-Thorbecke poverty index. And the idea is that we have two regions. We have an insufficiency region where people do not get enough of something, and a sufficient region where, okay, you can let the market play around, but I'm not going to try to improve your situation if you're already doing good enough. So the key word here is sufficiency. What we want to look at is this accessibility fairness index, which basically captures, okay, do I have access to a sufficient number of destinations, and SUF, from an engineering perspective, or not? So we take the maximum between it. Only if we have a deficit, it matters. Otherwise, if you are above it, you're doing well. Society doesn't need to provide for you, okay? We can relax it with a convex relaxation, and then we can sum it, we can put a square to capture the extent and the excess if you want, or not. There's different ways that represents different metrics. I'm not going to go into details. So that's very nice to frame. The only problem is this is a mixed integer quadratic program. We tried, and you can also ask Fabio, our server was not happy with it at all. So we need to find another way, because this is nice, but computationally intractable. And also, it doesn't really capture the relevance of which destination should be more accessible and so on, which opens a Pandora box, which I had the bad idea of opening discussing with Karel, but it's always motivating then to understand what you want to do. But okay, what we did, okay, let's follow still this sufficiency approach. Let's look at the extra travel time above the time threshold as a metric. So if you want to reach some destinations, if you can reach them if your threshold is 20 minutes, and if you can get there in 10 or 15 minutes, you're good. If you're above, that's a problem. So let's look at the extra travel time, this lag epsilon. We can relax it again, right? This is the travel time above the threshold. And then basically you can define the accessibility and fairness per region, weighting these extras with the flows, how many people want to do this trip. And then you sum over region with weight the population, and that's your accessibility and fairness index that we propose. And this is a linear program. So we can implement it. We did so for Eindhoven. We took data from Albatros, which is based on survey data, which trips are desired by the population, basically. On the right, you can see the clustered graph of Eindhoven, the intermodal graph. And some of the data, we set the threshold at 20 minutes, and we have a maximum number of cars. So we want to leverage these autonomous vehicles to provide accessibility, not to minimize travel time. But first, we took the vanilla intermodal problem and minimized travel time, and then checked the accessibility and fairness. And here you can see on a map, on a heat map, how it looks like. Right? Well, if you minimize accessibility and fairness, this is what you can do. So you can see you can reduce it significantly. In this plot, you can see the time-based model share, how many users are having which type of travel time. You can see in black the average travel time when you minimize travel time, and the threshold in green. So basically, these users here have an accessibility. Right? These trips are too long. If you minimize accessibility and fairness, you can get rid of it. And the travel time doesn't change. That's the surprising thing. You're not going against it. Right? Just another way of thinking, who do you serve first? Why? Well, basically just using cars that you were using for trips that were already short to cover a bit longer trips. Okay? You can see it also in these plots. So you go from having this situation, if you minimize travel time, you have in blue a fairly short trip by car. I think by bike it should take 5 to 10 minutes. And a long trip from Veldhoven, basically, to the center of Eindhoven that is covered by bike, that's going to take half an hour. That's not accessible. What you can do, well, take the cars from the first one, and they can go by bike, and actually cover as much as you can the second one by car. And that's a very nice idea. However, when we got these results, we thought, well, wait a second. We're saying that that trip is accessible, even though part of it, the bike path, is not accessible. It's above threshold. So what about path-based accessibility? So I think we need to revisit our problem statement. If you look at this, there is kind of a shadow on that term there. That term is basically the extra travel time that you perceive for trip M on average. Okay? But if you have multiple paths, then what? Look at this case again. Suppose the trip by car, 10 minutes. The trip by bike, half an hour, 50-50 the distribution. Well, the average is 20 minutes. We are below the threshold. It's accessible, right? But the bike path doesn't have accessibility. So what? And here there's two things you can do. First one is, or three. The first one was that I did was despairing, and then realizing it's actually quite interesting. It opens a discussion. If you look at if on average you follow these flows, one day you go by bike, one day an autonomous car picks you up, and you can even choose when to do that. Then you're actually getting average accessibility, right? Otherwise, if you really want to reason in terms of paths, but we saw these days, reasoning in terms of paths is a pain in the neck. So what you can do is to pre-compute possible paths. We did with and without MOD. and allocate flows to them. But it's a probably suboptimal approach, which actually works. So basically, you pre-compute fastest path. You can decide which one you want. You pre-compute the extra travel time, and then the only question you have here, okay, how many flow do I assign to the MOD path, and how many flows to without MOD path, okay? These are these two F flows, which are two scalars. And then we still have to decide the rebalancing flows, but the problem is significantly smaller. And we can solve it. And you can see here now, okay, let's go back. This is the average-based accessibility. So the first problem I showed you looked at it from the average. So on the horizontal, you see the metric we're looking at. If we look at the path-based accessibility of this result, however, that peak that you see there, it opens up. And the trips by bike are actually not accessible. If you optimize for path-based accessibility, you can actually resolve that issue, right? And what's happening basically is that you are saying, okay, this trip, the long bike path is not accessible, so I'm going to do everything by car and take them away somewhere else, okay? Make sense? You may ask, okay, what if we lower the threshold? Let's put the system more under pressure. If you do that, well, you can see you have even a higher peak with the average accessibility. These are the trips that on average are really on the accessibility, but if you look at the path-based, well, then the objective basically triples. It opens up. If you work in terms of path-based accessibility optimization, then you can lower this. And these two plots are always the same, because the path-based accessibility gives you the same average, right? You're really looking at paths. So what? So here are just two takes. Optimizing for this average accessibility results in a worse path-based accessibility, if you then look at the individual paths. However, if you could implement it, it would be the best thing to do, right? So if you could realize this maximum average accessibility, maybe with turn-taking mechanisms, would be great, right? You would give most accessibility to the system, and it's more a policy making. How can you achieve it? This brings me to the last part, just a couple of minutes. Suppose you have these two paths, and then you want to take, okay, the blue one, the fast one, when you're on a rush, and the red one when you're more chilled, right? And on average, you achieve an accessible travel time. How do you implement it? How do you make sure that you can implement it? You could use tolls, but tolls are not fair. You want turn-taking mechanisms. So what you can use are artificial currencies, something we started studying. The idea is very simple. It's a simple pricing mechanism. If you want to go fast, you pay. If you want to go slow, you receive points. You cannot exchange a point. You cannot buy them, right? It's something on its own, only for your mobility system. And this way, you can achieve it. And here are some results from other papers. When you don't do anything, you are at this so-called user equilibria. Travel time is higher than 30%. And as this mechanism kicks in, you get to the system optimum. It works. And also, and which is very nice, you are still free to choose when to go fast and when to go slow. So I would even argue your accessibility, but then, yeah, it's a very nice discussion we can open, is even better because you can choose. The day you're on a rush of less time, you go faster. The day you want to chill and you want to enjoy a half an hour bike ride, you can also do that. And you choose. And just looking at your portfolio of artificial currency. You can also do it for more arcs. And here with this problem, and you can check the papers, it's fascinating. Compared to static tolling problems, which are fairly not so difficult, let's say, this is super difficult. Because users need to think about the future when deciding, do I go fast or slow today? I have to look at what I expect to do in the future. It's at least a two-step decision process. Multiple arcs also works. Same idea. You can also, again, the fact that you can choose when to go fast and to go slow allows you to further minimize the perceived trip discomfort, okay? And you can also apply, we also recently studied this kind of pricing for equality and equity. Do you know the difference? So basically equality, you give same means to everyone, so it would be the left picture. I give you everyone a box. And equity, I give you the same outcomes. And depending on policy making, you may want to go for one or for the other. Suppose you've bought an electric SUV or a small electric vehicle. I could give you a fully charged vehicle in the same time. That's equity. Or I can give you the same charging power. And of course, the SUV will take longer. That's equality. And this, you can design prices for both, and they work. And hopefully at CDC and also CPHS, we will be able to present more. Last but not least, you could tell me, wait a sec, but anyway, you're basing this on user decision models. All these pricing things are based on a model we make of the users, but we know that models are wrong more often than not, and we don't really know how people would behave. There's been a very recent paper by ETH based on bidding schemes on this karma, which is a first step we need to do to understand behavior. But in general, if you implement something, your model will anyways always be wrong, and you need to tune it a bit. So what we did was to apply reinforcement learning to see, okay, can you adapt the prices? The answer is yes, it works, but the exploration phase, if you do it on a population, well, the third day, the system behaves in a funky way. The users say, okay, you know what? I'm not going to do it. So I would say to be continued. Now, in my last minute, I want to, because I also want to have maybe a question or so. If you like these topics, and by the way, thanks a lot for organizing this great session. We're organizing a conference in Eindhoven next year, an IFAC symposium on advances in automotive control, from individual vehicles to mobility systems. The deadline is November 14. Then you know what happens with deadlines. But keep this in mind for now. It would be great to host you on our beautiful campus and further discuss these topics. Now, to conclude, I think that raising awareness on transport justice challenges, together with the advent of new cyber-physical technologies, is giving rise to a new class of socio-technical challenges and opportunities. And I think that as control engineers, we have the right forma mentis, and also maybe responsibility to take a step back and reflect on what questions we want to ask and why, before engineering answers that ultimately will shape our future. And we have a choice. Looking at this picture, you see we have a choice here. You should remember, before being engineers, we are first and foremost humans. So look forward to bridging this transdisciplinary gap and contributing to science and ultimately and hopefully to society. Thank you very much, and I'm open to questions.
Thank you. Thank you. I think we have time for maybe one or two questions here, and maybe our next speaker can go ahead and start setting up.
Okay, thanks for the presentation. When you optimized for the average travel time, we saw that we can move all of that. You probably cannot show the graph again, but yeah, we saw that we can push all of the tail of the time distribution below the acceptable travel time. Or what was the trade-off in doing that? Like in engineering, there's always a trade-off. Or was that the model being wrong, considering the average accessibility and not the path-based one?
No, I think that the model is simply agnostic of the fact that there is a slight difference, right? There is a slight travel time difference if you look at accessibility, but it's not so massive. The thing is that covering different trips, you have different rebalancing actions, so you have less cars at your disposal that are providing this extra accessibility, right? So that's kind of the idea, but you're not really going against travel time. If you were to set the threshold to 0, you're minimizing travel time, or to a super high number, then with the regularization, so you're not going away, but you're being aware, oh, I can actually look at this dimension first, and then travel time. Yeah. Thanks.
Thank you. Let's thank Mauro once again for an excellent talk. Thank you.
Thank you.
It's now my pleasure to introduce our third speaker, Professor Andreas Markopoulos at Cornell University, who is, if you like what you're seeing so far, you have Andreas to thank. So thank you, Andreas.
Thank you, Rafi. Thank you. So again, thank you so much for coming to our session. You've heard so far a little bit about how we can use autonomous cars to improve traffic flow. Then we also look at multimodal transportation and equity. And next, in the next following talk, Yingqing will present how we can use connected automated vehicles to cooperate and have a fair transportation system. I'd like to believe that my talk will be the glue of this, in the sense that I plan to present to you a metric that we came up with so that we can quantify mobility equity in some sort of sense. So we've seen that emerging mobility systems like connected automated vehicles, shared mobility, electric vehicles can improve transportation efficiency. And we are about to transform, the transportation is about to get transformed to a new paradigm. We are about to move away from conventional vehicles with internal combustion engines and move on to pure electric vehicles. We will see vehicles being integrated with commercial and residential buildings so that we can have off-grid buildings. We will see the transportation network being upgraded with fast charging stations and having technologies that can dispatch the increasing electricity demand to different, in an efficient way. And on top of that, we have connected automated vehicles that can exchange information and can coordinate in specific scenarios that can improve transportation efficiency. So this is all the good news about emerging mobility systems. But the question that still remains unanswered is, can these emerging mobility systems also provide equal accessibility? Equitable transportation and accessibility remains a pressing issue as we speak. And this hinders access to essential services. There are underrepresented communities and communities who are economically disadvantaged that they do not have they don't have access to affordable and reliable transportation. There are urban areas where the public transportation is underfunded or poorly maintained, leading to not reliable transportation, and disproportionately, this affects low-income communities and minorities. So the idea is how we can measure equity. What will be the metric that can help us quantify equity? We are control theorists in this conference, and we like to have a metric that we can use to formulate a nice problem and optimize. So we need to find this metric. But before we get to that, we need to take a step back and look at what is transportation, right? Transportation is not mobility. The purpose of transportation is accessibility. Accessibility to services, to goods, to activities. Mobility is an unintended outcome. It just happened to be there, just for us, just to help us get to what we really want, which is access. So mobility is the means, after all. But at the same time, how we can measure accessibility? There has been several efforts in the literature to quantify and measure accessibility. There has been some more simplistic approaches that essentially take accessibility as the way that you can have the geographical distance between an origin and specific services, mainly employment. There have been some other efforts that essentially use isochrones that can capture the geographic areas that can be accessed within a specific mode of transportation within a specific time threshold. There has been also some other efforts that have introduced the accessibility index that takes into account the walking distance from an origin to a public transportation station and also the waiting times and so forth and so on. However, these efforts do not capture the disparity in accessibility that goes across different socioeconomic backgrounds and geographic regimes. To address this problem, there have been other efforts that try to quantify mobility equity. And you can see that there are typically two dimensions, the horizontal equity and the vertical equity. In the horizontal equity, the problem is to address equitable treatment of travelers with the same sort of needs, but they don't take into account any socioeconomic or geographic factors. In the vertical equity, the focus is to assess equity in transportation and essentially address the low-income based disparities in accessibility and mitigates mitigating the burden, the financial burden related to the transportation cost for low-income households. There has been also some other efforts in emerging mobility systems like shared mobility and what Mauro talked about, fairness. But still, there is a metric missing from the whole picture that can help us quantify equity and help us improve equity, as a matter of fact. So if we want to think about this metric, what would be the features that this metric should have? First of all, it should capture multimodal transportation, and in any city, on any different size, right? That would be the first asset. Then, of course, it should address accessibility, cost, but also some societal aspects of this case. And at the end, it should use only publicly available data. You can't really rely on a metric that depends on private information and private data. Regarding the data, the metric that I will introduce in a while, essentially we use two types of data, the point of interest data and the isochrones. In the point of interest data, we have geographic areas that they include all the type of services that you can find in this area. For example, groceries, financial services, medical facilities, restaurants, coffee shops, you name it. And then the isochrones essentially are maps that depict the areas that you can access within a specific mode of transportation and within a specific time threshold. So by superimposing the isochrones with the point of interest data, then you can have a nice map that can give you how many services you can access within a mode of transportation within a certain time distance. The picture that you see on the bottom is some isochrones from Columbus, Ohio, referring to bicycle for different time threshold, 10-minute bike, 20, 30, and 40. And you can see how many areas you can capture by using this. And this is another example of a superimposed isochrone with a point of interest in the Boston metropolitan area. You can see that the black lines corresponds to the neighborhoods in Boston. The green line corresponds to the area that you can access within 30 minutes drive, assuming that you have a free flow on the driving. And you can see inside this green area how many services you can access. So another good thing with isochrones is that we can use different modes of transportation on the same isochrome. So this is an example, again, in Boston, using 4 modes of transportation: walking, cycling, driving, and also public transportation. And then this is, of course, in 2 different time thresholds. For the walking and cycling that you can see in the map, we used a 10-minute threshold. For the driving and the public transportation, we use 20-minute threshold. So this is a nice feature, and this is also the way that you can see how many services you can access with walking, cycling, driving, and public transportation. So that's the first step. But that's not enough. What we're missing is now we have to enhance this information with some sort of cost and societal factors. And again, we need to measure how much will cost us to get access to these services within this time threshold and with this mode of transportation. And we need to translate this into the sort of cost per passenger per mile. But again, this would be not enough, because if I say that, if I know that I need to spend X amount of dollars or euros to use taxi and get access to these services, how do I know that this is affordable for everyone in the community? So we need to inject some sort of sensitivity in the pricing, right? And at the end, we need to prioritize on the services. Not all the services are equally important. Medical facilities or financial services or employment, schools should weigh more than entertainment activities, venues, recreational activities, or restaurants, and so forth and so on. So with this in mind, we introduce the so-called mobility index in a given transportation network, where essentially for a script set M that includes all the modes of transportation, walking, cycling, driving, public transportation, you name it. And for a given script set S that includes all the type of services, medical facilities, pharmacies, grocery stores, restaurants, coffee shops, and so forth and so on. And we have also a set script O of all the neighborhoods in a given metropolitan area. We call this, mathematically, we represent this with nodes. We introduce the mobility index. So the mobility index will give us the sort of notion of affordable accessibility. And I will explain in just a minute what I mean by that. First of all, the second term give us the weighted sum of the services. The notation sigma IM of S is the number of services that we can access with a mode of transportation M within the time threshold tau M. So this is the number of services. And then we multiply this by beta S. Beta S is a weight that we can give priority to one particular mode of transportation, service versus other services. So if beta S is higher, it means that these particular services have higher priority compared to others. And then we multiply this by another factor that gives us the sort of impact of the cost. Cm is the cost of transportation M in passenger per mile, and then Ki is the sensitivity of this cost to the residents in the neighborhood I. So for example, if Ki is high, this will give you a higher mobility index to those modes of transportation that have low cost. So Ki will promote low-cost transportation. And if you think about it now, with this mobility index, if the mobility index is high, it gives you the sense of affordable accessibility because it promotes those modes of transportation that have low cost, but at the same time gives you access to many services given this structure. These are some examples. We did a case study using, again, public transportation data in different cities like New York City, Los Angeles, and Philadelphia. And you can see how the mobility index is higher as the colors are darker. You can see the areas that are close to downtown have the higher mobility index, which is what we expect to see, in the sense that in the downtown of these cities, you have a lot of services, you have very dense transportation, public transportation network, and that's why this is promoted. And actually, since we don't have a basis of comparison with other metrics, right? This is a metric that we constructed. We look at the perception of these cities on the transportation, and the index, the values of this index sort of align with this perception. This is another set of data with Chicago, Washington, D.C., and Boston. So, and we see the same pattern, right? Now, this is, and we have another piece of data. Just to connect a little bit the dots, we plot the normalized mobility index with respect to distance to downtown. So as you see, as we move away from downtown, the mobility index drops for these particular cities, Boston, Chicago, DC, and Philadelphia. And then we compare this with two other metrics. We sort of found out the normalized number of services, and then as you move away from downtown, these services getting smaller, so you can have access to less services. This is, of course, what we expect. But we also plot out the normalized income of the residents in this neighborhood with respect to distance to downtown. And we've seen the same trend. And that was encouraging because now you can see the value of the KI factor that we have in the mobility index. If you remember, the higher the KI, the more sensitive to the transportation cost. And this kind of brings the mobility index being aligned with the income of the residents, in the sense that if you put the right index Ki on the mobility index, it can capture the implications of transportation mode to these particular neighborhoods, which by the way, they have no high income. But again, this is the mobility index can capture affordable accessibility in specific neighborhoods. What if we want now to see how this is fairly distributed in big metropolitan areas? Like, let's say we have neighborhoods in Boston, we want to capture the whole area of Boston metropolitan area or the whole state, perhaps, and similar to other cities. To do that, we use the Gini coefficient. The Gini coefficient is a measure of statistical disparity, and it's been typically used to capture the income distribution in the country's population. So what we do here, Gini coefficient can take values between 0 and 1. If it's 0, it means that it's absolutely equally distributed, right? If it's 1, it means the opposite. Now, we kind of modify the Gini coefficient index in the sense that we want to inject the mobility index and see how this mobility index of each neighborhood is fairly distributed across the whole metropolitan area. So to compute the Gini coefficient, we use the Lorentz curve. It's A over A plus B. If the area A is 0, it means that you have the absolute equal distribution of all the mobility index, and essentially the Lorentz curve corresponds to the line of 45 degrees. If the area A captures the whole triangle, then it means that you have the most unequal kind of distribution of the mobility index. So given this mobility Gini coefficient, we introduce finally the mobility equity metric, which is 1 minus this ratio, the Gini coefficient, where essentially if the Gini coefficient is 0, it means that you have perfectly equal distribution of mobility index, which means that the mobility equity metric is equal to 1. If you have the opposite, you have 1 minus 1, it means that the mobility equity metric is 0. So with this kind of approach, we capture the mobility equity metric, which, in summary, gives you the affordable accessibility as being distributed across a big metropolitan area. We computed the mobility equity metric, the MEM, for different cities in US, using, again, publicly available data and the census. And these are the plots that we got. And we try to see the perception of these cities, across the lines of the modes of transportation and mobility, and it was pretty much aligned. Of course, we don't have basis of comparison to compare against other metrics, because this is by construction, but at least it gives you, given other metrics that exist in the literature about some of these cities, you can see that there is some sort of alignment. We also built an online platform. Of course, it's not complete. This is work in progress. This is available online. You can visit it as we speak. Essentially, what we did, we captured New York City, Boston, and DC, and we tried to compute the mobility index metric and also the MEM. So you can go there. The whole vision behind this platform is, first of all, to include as many cities as possible in the US, and perhaps later on in other countries, in other cities in other countries. But we envision this to be kind of a tool for city stakeholders, which they can go and play around with the different metrics of mode of transportation, cost, and see how they could potentially make some informed decisions about the different modes of transportation. So as I said, this is a work in progress. We plan to, and we hope to have it done by end of the year. And of course, I will promote this in social media so that you guys can get informed about this. And now, given this metric, and since we're, as control theorists, we are obsessed with metrics, now we have a metric and we can sort of formulate a nice optimization problem, and improve. I'm not going to get to this discussion. I just want to give you the complete picture. Essentially, what we can do here is we can use vehicles that you can, let's say, we can assume that they are complying with what kind of routing suggestions we would give. And if, let's say, if we want to think of what would be the compliant vehicles, that would be connected automated vehicles. These are computerized vehicles. We can control them, public transportation. And for non-compliant vehicles, vehicles that we can perhaps suggest some routings, but they can completely ignore, that would be private owned vehicles. So, and given this, you can formulate a problem and try to optimize the routing with the objective to maximize MEM, right? So this is another one of the potential dimensions that you can somebody can take using this metric. So to conclude, the whole idea is to come up with a metric that can sort of capture affordable accessibility fairly distributed across a metropolitan area. We did some case studies to see how this metric captured this, of course, by backing this up with some sort of perception of other cities. And we are building an online platform that can help us see the picture of this city. Unfortunately, as I said multiple times, we don't have a way to compare MEM and say, okay, this is a good metric that capture. We just use rationale and try to build up and create this metric based on aspects that make sense. But we are so looking forward to your feedback. We have a couple of papers out, yes. First of all, these are the contributors for this effort, my students and my postdocs. We have one paper that we will be presenting next week in CTS, another one that is going to be presented in ACC in Toronto, and the third one has been submitted. So, I hope you get a chance to go through the papers, and we'll be more than happy to hear your thoughts, any suggestions, and how we can potentially revise this metric and make... we already have one revision. In ACC paper, instead of the Gini coefficient, we used the average. So we took the mobility index and averaged across the area. And then we thought that it doesn't really make sense. We can't really average because, And then we came across the Gini coefficient, and we thought that this is more appropriate. And in the CTS version, we use the Gini coefficient. So you can already see a couple of revisions. I would like to acknowledge the financial support of an NSF who has funded this work. And with this, I would like to thank you for your attention. I'd be happy to take any questions.
Thank you, Andreas. That was really interesting. We have some time for a couple of questions. So if there's any questions, please wait for the microphone. It looks like Mauro was... Oh, I don't know.
I can put...
Yeah, you're on.
Yeah,
great.
Wow, that's
Thank you.
So technological. Thank you. It's a super nice talk. I really liked it. I wonder about this index. How sensitive is then to the parameters? Because I've seen there are many, especially the one related to cost. You want this kind of decay.
It is sensitive. It is sensitive, and we try to quantify this sensitivity with multiple, using data. It's sensitive to data, but it sort of gives you, since you take this across different neighborhoods. Imagine that, let's say in Stockholm, you have so many neighborhoods. So if you take this, you can give you the big picture. The mobility index is just a dot, just a neighborhood. You need to define how big you need this neighborhood to be, right? But then you take this and you sort of use it, apply it across different neighborhoods, and then you can sort of see the patterns, the colorful patterns that gives you a sense of, and then you can tell, okay, now this is this way, the affordable accessibility is that way, distributed across the whole this neighborhood. But this is very fresh work. We still need to understand a little bit more about the sensitivity of the index, how it works in different set of data. Data are not always, you have some noise. So there's still, we still have a lot to understand in this.
No, I think, indeed, what I said before, I think it's any step we do in this direction is already great. So this is, I had another small question, if I may. Did you compare, I said, so you did also some work on applying, leveraging this metric as a good engineer to kind of figure out, okay, what if we do in that direction? What are the benefits of looking in that direction compared to if you don't? If you do like standard time minimization and so on, and did you see a big difference, or?
So yes, actually, I was seeing your presentation that you use, and I think you can find the same trends, different absolute values, but the same trends. And the reason is that if you recall, in the mobility index, you capture number of services, you capture travel times, because you have the time threshold, which designate essentially the area. You have cost, but you also have the sensitivity of the cost, because some neighborhoods, let's say you focus on the mobility index on a particular neighborhood which has low-income residents, households, then you can have you can assign high sensitivity on this. Now, somebody might ask, okay, how do you assign this? You need to make some decisions, right?
Did you talk with policymakers?
Right. So essentially, I would say that somebody from a policy scientist might be more appropriate to adjust this, but at least you have control knobs to adjust, and now how to define this. And then one other thing that I didn't mention in this presentation is that you see you have multiple services, and these multiple services, and we have also multiple modes of transportation, and we weight this. And then the problem formulation that we have is about finding the optimal values of these weights on the modes of transportation to improve MEM. And what ends up happening is that you find in the solution that you have high values on the weights about public transportation, because it's the most affordable. So you prioritize on public transportation or other modes of transportation like cycling, which has low transportation cost.
Great. Thanks.
Yes.
I think you were first, and then the microphone will work its way down to you.
So thanks a lot, Andrea, for the great talk. So I have sort of like a provocative question.
That's what I like.
So you mentioned at the beginning, transport is not about mobility, it's about accessibility. And then you introduce a mobility index.
Absolutely. So, I mean, this is... I can blame on this my student, who is the godfather of this name of mobility index. I mean, I just go along with whatever they come up with. So, but I agree with you. I think it will be more appropriate, since this is essentially affordable accessibility, at least this is what it is.
That was my question then, because I was going to disagree. I like the mobility index instead of accessibility, because with accessibility, then you put online. Basically, and then we are worse off, because this conference, all conferences would have been online.
Yeah.
Because that's the most affordable. You can travel from wherever, and that doesn't capture that.
I think as long as we understand what kind of information it provides, I think we can,
But I'm sure people who want to promote the online and stuff, and I've seen it in other conferences, saying, I mean, the cost and the pollution that has been created for people to come to congregate and come here, because many people took a flight, airplanes have a lot of emissions and all these things, and if you put that into that, then probably the cheapest way to stay home and telecommute or everything, do it remotely.
Absolutely, you're absolutely correct. And by the way, since you mentioned environment, we working on enhancing this with sort of environmental impact. So we have accessibility, you have equity, but do we have any trade-off? If we try to improve equity, do we sacrifice environmental impact, or they can go along? So we try to kind of enhance that with that factor. But going back to Stelios' comment about the name, it is affordable accessibility. At least this is, in my mind, how I can explain this. But it is called mobility index, thanks to my students.
On that note, let's thank Andreas again,
Thank you.
our speaker and the organizer of this. Thank you. I'm going to introduce the last speaker today. Yingqing Chen at Boston University. I understand you're going to talk a little bit about cooperation with automated vehicles and bring it back to traffic. So please, the floor is yours.
Thank you. So hello, everyone. My name is Yinqing Chen from Division of Systems Engineering at Boston University. And this is co-work with Professor Christos G. Cassandras and Annie Lee. So today, I'm going to share the topic about achieving social optimality in mixed traffic mobility coalitions and cooperation compliance. So in recent years, the concept of this Internet of Cars has gained traction, promising a new era of connectivity and efficiency in transportation. And this is all powered by this connected autonomous vehicle, CAVs, which provide a game-changing opportunity from the selfish driver optimal to the social system optimal. So we can imagine a world that there is no traffic lights and no stop, and traffic flows pretty smoothly and efficiently thanks to these real-time cooperations. So in order to achieve that, we also have made some efforts. Like this is our simulation testbed called MCT, which includes many conflict areas such as the roundabout or the highway segments. So we focus in this work on this lane-changing behavior as a typical application to address the importance of cooperation. So as you can see in this real picture, please let me merge before I start crying, that in real world, we all have times that we need some cooperation. We want to achieve this lane-changing maneuver. And many previous works focus on such maneuver as listed here. But however, some of them assume 100% CAV penetration, and some achieve no social optimality. So it's true that the introducing CAVs to our existing transportation network can improve the safety, reduce congestion, and energy consumption. But these all benefits are shown based on a big assumption of 100% CAV penetration. And it's safe to say that it will take at least several decades for this to be realistic. So therefore, incorporating human-driven vehicles, HDV, into our analysis is necessary. So that's why we call it mixed traffic. So there are 3 ways to go for the mixed traffic scenario, like perception learning for better HDV models, like safety prioritization, and the cooperation compliance mechanisms. So in this work, we decided to study the mixed traffic in lane-changing maneuver as a common conflicting area in the transportation network, in which we want to develop a cooperation compliance mechanism while enhancing safety. So the key idea for this is that vehicles can cooperate to achieve desirable performance. So in order for that, we first step is to create a candidate set to merge, which is often to be like 4 to 10 vehicles. And we evaluate where to merge. So once we have found the optimal pair, or we say the triplets, we can optimally control the CAVs in the triplets in order to minimize the travel time, the energy consumption, the traffic flow disruption, while guarantee safety. The safety is most important. And note that the concept of traffic flow disruption is pretty new and important, since that it's able to capture the global effect of lane changing. For example, if this CAV-C wants to merge between these 2 purple CAVs, 2 purple vehicles, so the latter one is highly possible to decelerate, and all the vehicles behind may be affected. So the traffic flow disruption can capture such effect, and you can see detail in this publication. So this is the basic optimal control problem for that, why we optimize time, energy, and speed disruption while following some dynamics, constraints, limits, and safety constraints. And we will solve this OCP for any CAV-C defined in this traffic network. But specifically, in a mixed traffic scenario, we will consider triplets like this, where a CAV-C is drive at the slow lane while he wants to merge into the fast lane, and there is an HTV at the fast lane following a CAV. So we consider this setting because this back vehicle is critical for this cooperation. Like if the CAV1 is at the back of the HDV, it makes this problem much simpler because 2 CAVs can cooperate with each other. So, however, our case is more complex. So we Like consider we have a binary choice for CAFC. The one is to merge ahead of HDV, the other is to merge ahead of CAFs. So we want to determine the optimal control and cost for both two cases. And note again that in case 2, the HDV behavior is irrelevant. So to get such control for both cases, we define OCP for all 3 vehicles. Firstly, we consider a simple second-order dynamics, and with which we can define a speed-dependent rear end safety constraint. For example, see the first constraint, we want the distance between the CAP1 and HDV to be larger than some reaction distance plus a minimum safe following distance. While this reaction distance is composed of reaction time, which also takes a value of 1.8 seconds in many works, and times this velocity of the latter vehicles. And in the third block, we also have some vehicle limitations. So we start with the case 1 that this CAFC wants to merge ahead of the HDV. And this is pretty challenging because the HDVs are uncontrollable and they may not yield to CAFs. So we divide the whole process into 2 phases. The first one is for CAFC to accelerate to reach H, and we denote the time that HDV and C are parallel as T1. And phase 2 is starting from T1, and we solve a lane changing problem by solving a bi-level optimization problem, and while estimating the HDV behavior. So we're now explaining in detail how these 2 phases functions. So first, for phase 1, we want to find the optimal trajectory for C to reach H, while we find the optimal time, T1, as defined earlier. So in order for that, we want to solve an optimal control problem that would optimize the travel time, control, and speed deviation, while we want the terminal position of 2 vehicles to be the same. Yeah, but it can be infeasible when CAFC don't have enough time to catch H. So in that case, we can simply test this extreme case by speeding up with the maximum acceleration. Or the CAF1 can help CAFC by decelerating to force HDV to slow down. And we evaluate the energy and the speed disruption for both vehicles in this case. So in summary, we find the minimum cost of these 3 ways, and we calculate this optimal end time and optimal trajectory. So we note again that this time, T1, is also the time that HDV is aware of the intention of CAF and start to behave accordingly. So starting from this time, we enter the phase 2 and start to calculate the true cooperation control. So the ideal trajectory for CAFC is to assume that HDV drives at a constant speed until TF, which we denoted at the terminal time of the lane changing behavior. But we know that this is not possible in practice. So in that case, we formulate a bi-level optimization problem with the vehicle interaction, and we solve it with a iterated best response IBR methods, as you can see in this flowchart. Like we initialize with the trajectory from the ideal case, as just mentioned, and based on that, we solve an optimal control problem for HDV by assuming that the human drivers would consider these 3 factors: the collision risk, the energy, and traffic flow disruption when they decide to drive. And the CAFC and then the optimal trajectory is calculated and transmitted to CAFC. Then CAFC can respond to it and again calculate the optimal trajectory and transmit to HDV and CAF1 again. And they're solving a similar OCP for that, but except for the CAFs don't consider the collision risk because they are like CAFs. And all these procedures would iterate several times until converge to some final best trajectory. So we would detail the mass formulation in this page. And for HDV, we assume that the driver wants to minimize the energy, as you can see, the control, the speed disruption, and this collision risk. And we represent this collision risk by a risk function S. And this function is decreasing as the distance of gap between two vehicles increase. In our work, we use the sigmoid function for that, but it's actually like learnable for each driver from their past driving behavior. Like, for example, some drivers are more aggressive than others, and they are willing to take like smaller distance gap. And we have a similar OSAP for two CAVs, except for their terminal state and safety constraints are different. And in terms of the convergence, we declare that this IBR process would converge in finite time, and this is proved theoretically in this work. And actually, in our test, the average iteration for the convergence is just about 4 or 5 iterations, so it's pretty controllable. So until now, we introduced how we can control under the case 1. Then we will start the case 2, which the CAV-C wants to merge ahead of CAV-1. So this is an easier case since the importance of HDVs are downgraded. So by applying this choice, the safety can be guaranteed since CAV-1 is cooperative, and we don't need to consider the behavior of HDVs, and which makes our calculation simpler and actually can be solved analytically. But it will consume more travel time because the CAV-C wants to take more time to get ahead of CAV-1. So we have the similar formulations for case 2, and it can be solved analytically again. So until now, we have detailed the controls for both cases. So the possibility of 2 options makes us to wonder like which to choose, where to merge. So the most reasonable way is to like calculate the cost of 2 choices and choose the one that with the lowest cost, which is most reasonable. But we can even find an easier policy by observing their cost formulation. So we called it this optimal threshold policy. And firstly, we denote the distance between the CAV-1 and HDV as D, and find that the total cost for merging ahead of HDV, the case 1, is independent of this D. But the cost of merging ahead of CAV-1, the second case, is monotonically increasing in D due to the long travel time and therefore acceleration and speed change. And actually, we have proved that analytically in our work, which is also like in accordance with our intuition. So therefore, we can have a threshold theta that if the D is smaller than this theta, we choose to merge ahead of CAV-1, and otherwise we choose case 2. So this is a simulation plot for the cost of 2 cases. We can see the blue line is the cost of merging ahead of HDV, and the red dotted line is the cost of merging ahead of CAV-1. So there is an intersection here. So we say there exists an optimal threshold, which is just the intersection dot on the distance between the CAV-1 and HDV that determines the optimal choice. We have more simulation results for the detailed control trajectories. So the left columns is the state trajectory of the 3 vehicles in the triplets under case 1, and the right column is for the same trajectories under case 2. So for case 1, we start from the speed. You can see the CAV-C, denoted by the red curve, would increase, and which is following the phase 1. And at the time t1 equals 3.54 seconds, the position of the CAV-C and HDV is the same, means the termination of the phase 1. And then after that, the CAV-1 start to speed up. As you can see, the blue curve start to speed up and make some room for CAV-C, which is like in accordance with our intuition. And for case 2, the CAV-1 start to decelerate to make some space for CAV-C, while the CAV-C, the yellow one, would accelerate. We also note that this HDV would also forced to decelerate a little bit. So, and for both cases, at the end of the maneuver, the gap is sufficient for each pair of vehicles. So we say the safety is guaranteed. So we then compare the control in the mixed traffic scenario with the 100% HDV environment case. So we state it as a baseline, which is basically using the standard sumo car following model. And we can find the total cost, the disruption, and maneuver time are improved using our framework. So up to now, we have formulated a lane-changing problem on mixed traffic scenario, where the HTV would behave in response to the surrounding environment for its own purpose or efficiency. But we now start to wonder, like, what if instead of passively responding, what if the human driver vehicles can actively choose to cooperate with other cabs to create some social compliance? So here comes to our second part, the cooperation compliance. So to achieve the cooperation, the first question is why would they cooperate? What's the incentive for this cooperation? And specifically, if we consider this scenario of this figure, that this CAFC wants to merge between these two red vehicles, so why the vehicle 2 wants to decelerate and make some room for CAFC? So to address this problem, we use a concept called refundable toll that has been brought up in many previous publications. And the key idea is that every driver owns a digital wallet, and users commit a number of tokens at the start of each given period, such as they pay a toll. And these tokens are virtually and can only be used within some given market, in our example, the transportation market. And this is fully refundable as long as the user complies with a set of rules. And these rules can be different at different scenarios. For example, if we're considering a routing problem, when a social planner provides some reference routes, the rule is just to follow the route. But in our lane changing case, the rule is to accommodate lane changing from a vehicle in the slow lane when such request is received. So in order to evaluate how much the rule is satisfied, we first define a variable for compliance behavior score, which is chosen to be inversely proportional to the deviation from the actual states of agent I and the reference states by social planner. And to make it simple, we make it binary, which takes a value of 1 if the user complies at time k, and takes value of 0 otherwise. But actually, it can also be continuous variable indicating some partial compliant. So with the compliance defined, so we have another compliance rate, which is the probability that driver I cooperates at time k. So with these two variables, we now introduce the cooperation compliance control framework for that. You can see this flowchart is our framework. Assume there exists a social planner that would send the reference to both the non-compliant agent and the compliant agents. And in our case, the non-compliant agent refers to a human-driven vehicle, which might choose not to follow the reference, while the compliant agent refers to cabs, which are designed to always follow the reference. So in addition to the reference, two kinds of controls are sent to both agents, to induce them to comply with the desired reference. We have a global cost that is for every user towards a global optimality, and we have a local cost designed for each user I as a penalty when they are not following the reference. So after receiving these controls, these two costs, the agent would then behave accordingly, and the compliant agent would send their states back to the social planner. Then the social planner would update this cost accordingly in a feedback control way. So we're now introduce this feedback control as here. The equation states a simple scheme that the global cost is added at each time step by some difference between the desired compliance rate and the average of compliance behavior of each agent. And such average is replaced by a decaying time average for the local cost. And the compliance behavior score of agent I, this MI, is actually measured based on some arrow, and which is the discrepancy between the reference state and the true state. So the arrow can affect the compliance behavior by negatively proportional to some maximum tolerance of state rate. And this is intuitive because when we have higher arrow, we have lower compliance behavior score. So with the updated compliance score, we can update the global and local cost. And then the behavior of the non-compliant agent would then be affected by those costs because they're cost sensitive. And the level of effect is represented by an attribute called compliance probability that we will introduce now. So this is the compliance probability. So it is non-decreasing function of 3 components: the initial proclivity for I to comply, and the global and local cost. And we assume this function P to be piecewise linear at this format, but it actually can be different for each driver, indicating their driver preference and their sensitivity to cost. And it actually can be learned from their demographic data and from their past driving behaviors. So with this equation, we can calculate the compliance probability of agent I after k time steps. And with this updated compliance probability, we can modify our OCP for HDV, as I was saying now. So this is the modified cost function for HDV problem. So since the deviated behavior would be penalized by the social planner, so the human driver must take the penalties into account. So for this cost function, we have 2 parts. The social goal is to minimize the control difference from the reference. And we have a selfish goal to minimize its own energy consumption and speed deviation. And they are all weighted by this cooperation compliance probability, capital P. So subject to the dynamics, the vehicle limitation, and the safety constraint, the OCP is solved to estimate the real trajectory for HDV when its compliance probability is this capital PI. And for CAF, we can solve a similar problem, except for this PI is equals 1, because we assume the CAF is fully cooperate. So now we present an example showing the performance of our framework. So we consider a scenario in this figure where the green vehicles are CAF and the red vehicles are HDV. And this CAF-C wants to merge in between the CAF-3 and HDV-4. So under this setting, we calculate the control through our framework. And there is a resulting plot for the trajectory of compliance behavior, the global cost, and this local cost, respectively. So we start from the first plot of compliance behavior score. Note that compliance behavior score M is decided by the difference between the actual state and the reference state. So we can observe this purple line. This H stands for the HDV4. It's actually non-compliant initially with M equals 0.65, but it starts to increase and converge to a full compliance due to the increasing of both global cost and local cost. So the compliance convergence proves that our framework can induce the cooperation compliance behavior of some initially non-compliant agents. So up to now, we have presented the lane changing control in mixed traffic and the potential cooperation compliance control framework that it can incent the human drivers to cooperate with CAFs to achieve a high level of cooperation in lane changing case. So here are some potential future roles that we can work on the models that can like predict better or learn better, or we can explore deeper level of coalitions against uncooperative agents and to hopefully achieve a higher level of cooperation. So that's it for now. Thank you.
Thank you very much. I think we have a couple of minutes for some questions, if there's any questions from the audience. All the way in back.
Yep. Thank you for the very interesting presentation. I was just wondering, I'm not sure if I missed it. Both cases, we're assuming that there is no lane changes from the upper roads to the lower roads. Is that correct?
I'm sorry, I didn't quite.
So in this case, we're considering the CAVs merging into this upper road, right? I was just wondering if you or the lab has considered a case where there is lane changes from the upper road to the lower road, because the assumption on the case 2 where the CAV on the lower roads going in front of the CAV, it says that the behavior of HDVs are irrelevant. But if there is a lane changes, if its CAV slows down, maybe HDVs, because we know that their behavior is irrational, they might perform lane changes. In that case, I think the HDV's behavior might be relevant. So I was just wondering if that assumption has been made or if those will be considered in the future works.
Okay. Yes, currently we only consider triplet like this, and these are solved like decentralized, and each triplet will solve a similar problem like that, and we assume actually that human-driven vehicle would not make this lane changing while they have make the lane changing to the fast lane. Yeah, this is the assumption. Yeah.
Other questions? If not, I had a question. So part of this relies on this sort of estimating the probability that the human drivers are going to comply.
Yes.
Right? So you briefly mentioned that. But I was wondering if you could elaborate on that a little bit. Like over what, is this like every driver has like a sort of a compliance score over the last 1,000 kilometers they've driven, or is this more like a right now in real time you're updating based on their last couple of seconds of driving? I guess like what's the, how would that happen? How would that work, right?
Yeah. We actually have two costs, global cost and the local cost.
Okay.
So we have a local cost which measures the long time, the time average behavior of this like human.
So over their entire driving history, over the last years, over some long
maybe
time.
Over this trip or over like previous records.
Okay.
Also we can take into account, and we have a global cost to make every drivers to work better in the next trip.
Okay.
Yeah.
Okay.
So from past to next.
So okay.
Yeah.
So both sort of like a longer horizon and a short horizon.
Yeah.
Thank you.
Thank you.
Well, with that, I think we are out of time. I do not want to be the one to hold you back from lunch. Thank you, everyone, for joining today. And thank you to our speaker, last speaker this morning.
Thank you.
Enjoy the rest of the conference, and thank you.